So, do you want to do some brief introductions at the start and welcomes? Would that be okay?
Okay, so welcome everybody this afternoon. As you know, this is the first day of Chinese Lunar New Year. So Happy New Year to everyone. And it's great to have the first ACE Network ECR event. And this is based on the theme of aging society. My name is Ziwei Wang. I'm the lecturer in robotics at Lancaster, as well as the same lead of ECR of the aging society theme. So so now it's your time, Mike, and you can take my microphone and go ahead.
Okay, thank you very much, Zoe. Thank you for the introduction. So, welcome everyone to this webinar, which is primarily linked to one of the main sub-themes within the ACE network. I'm going to give a very brief overview initially of the ACE network and thank Kate very much for putting together some of these slides across the network. So, thank you for that. So, what is the ACE network? Automatic Control Engineering Network. It's a 3-year funded network funded through the EPSRC, which began just over a year ago, 1st of January 2024. And the concept here is to bring together an interdisciplinary community, effectively to help create more visibility and drive forward research and innovation in control engineering across the UK. Now, we want to ensure control has been a major player within UK universities and industries across the years. We want to ensure that the UK continues to maintain global leadership in that field and at the same time address current global challenges. So, as I've already mentioned, the UK has for many years had a strong control engineering community, but perhaps in more recent times this has become less visible and less influential in terms of policy making and research funding. And as we all know, control engineering has been instrumental and will continue to be instrumental in having a huge impact on society in so many ways. Yet, compared to other disciplines, which seem to be more at the forefront in terms of their visibility, it seems to be less recognized compared to some others. So we feel that control engineering is key to advancing AI, something that, as we all know, the government is pushing for at the moment in terms of support for making the UK a European AI hub. And control engineering is a core component of AI and its development. But at the moment, this seems to be obscured more by large language models, so more of the textual concepts and areas. So other disciplines have increased their share of research funding over the recent years. Whilst this doesn't seem to have grown, it seems to have reached an equilibrium or steady state for control and hasn't increased. And we want that to change. So we're not reaching out to the younger generation as we have perhaps been in the past. And there don't seem to be as many undergraduate control engineering courses and departments available or within academia these days. So we want to place control engineering at the forefront again in terms of engineering and make it a key component within engineering degree programs and with support for industry as well. So, as is well known, the UK has a proud history of such contributions within this field, and we want to do more to try to help create and support future leaders. So, who's supporting this? Well, this whole project is actually the leads are Daniel Coker from Newcastle, formerly from Sheffield, as you may know, and Antonis Papakhristodoulou from Oxford. And they drove the initial proposal and have engaged a number of us to help support this network moving forward. Fortunately, we have the backing of the UKACC, Automated Control Council, and with 200 plus members who've already signed up to express an interest in the activities that the network is scheduled to undertake across different areas. There are also industry partners, which cut across a wide range of industrial sectors. The more the merrier. So if you know of others who you feel may be interested to be involved with this network, then please just let us know or get them to sign up as interested parties in the network. Now, these areas include manufacturing, engineering, healthcare, transport, automation, IT, etc. But there could be others. And the network has also secured support from key UK catapults as well. So it's widening its web, and we want to make it that web as wide as possible. So here are some of the network partners. I won't go through and list them all, but clearly some very key players in there. And the more industry collaboration that we can engender, the better. So if you know of people or you're not signed up to the network already, then please do contact us. So basically, what are the outcomes we hope to achieve? Well, we want to create an interdisciplinary research community which is connected, engaged, knows what's going on, and it works with key stakeholders and can help to support major societal changes. So in terms of the vision and the long-term goals, the priorities are for research and a plan for how control engineering can and will contribute to societal changes in the future. So within this, we want to create technology roadmaps, mapping both short and long-term industrial needs, with specific control engineering solutions at the key and at the core. And key to that, game-changing recommendations for policymakers for the future. So at the moment, this is very much a virtual center of excellence in terms of automatic control, but we want to ensure a lasting and sustainable legacy beyond the initial funding period. In order to do this, not only through the events that we're hoping to hold in the next 2 years, we also hope to increase grant capture and undertake multidisciplinary research, engaging industrial collaborations, knowledge exchange, and long-term research collaborations which will run for many years to come. So these are the grand challenges, the 4 key grand challenges that are inbuilt within the ACE network. There is AI and data, clean growth, future mobility, and you can see the various areas. And today's main topic, the aging society, where we'll be looking at the control of biological and medical systems, human-machine control systems, systems and control for societal impact. So whilst this is today's meeting is targeted towards the aging society group, then please feel free, if you're interested in the other groups as well, to make that known to us. So just looking back a bit in terms of UKRI strategy with regards to the aging society, their main ideas have been to develop or to develop products and services that help people remain independent and active into an older age, as more of us live longer due to technological and medical advances. So key support areas and innovations in terms of societal challenges are linked to creating healthy, active places designed for age-friendly homes, smart homes, living well with cognitive impairment, managing common complaints of aging, which may be more prevalent as more of us become older in such a society. Also, maintaining health and work and being able to stay in work for longer periods of time, now that retirement ages seem to be extending yearly. And supporting social connections, as well as sustaining and being able to sustain physical activity, keeping active, keeping well, keeping fit. So the Aging Society Grand Challenge Research Group, we hope will empower an aging population. I've been asked to chair this group. I'm based within the School of Engineering at the University of Warwick and lead the Systems and Information discipline stream there. My co-chair is Professor Lucia Marucci from the University of Bristol, and Ziwei has kindly agreed to also be a member of our management team moving forward. So this is just one event that aligns with this group, and we hope there will be more, and as we'll see as we go through the meeting, other events that will be planned over the next 2 years. So the network ACE is at the forefront of developing technologies that will enhance the quality of life for an aging population. So we want to apply control theory to biological and medical systems And the network hopefully will allow us to revolutionize healthcare, enabling independent living and supporting social care. So underlying this, there's the intention to create smart environments that will be able to cater for the needs of older adults. From simple systems such as controlling heating, lighting, etc., security systems within smart homes to optimizing public transport and accessibility. And alongside this, there is the desire to enhance independence and well-being for those of more elderly years. So the network and through our group is committed to working with technology developers and policymakers in order to allow us to achieve this, to address the challenges of an aging population. So we want to leverage the power of control engineering and create a future where older adults can live, especially with dignity, independence, and vitality. So those are key factors. So some potential research areas that we've identified, in particular in terms of the application of control in this field, are, say, wearable health monitoring devices, human-machine interfaces for assistive technologies, optimization of drug delivery systems, and compliance with the taking of medication, which is a key component in that field, compliance. Control of robotic rehab systems, design of smart home environments which are not too invasive and accepted by elderly residents, and the optimization of healthcare resource allocation through control-based modeling and simulation. So using the power of modeling and simulation to enable us to develop these tools. So these are some of the planned activities. Some dates are yet to be fixed. The first of these after the formal launch, which is taking place in March at Oxford for the network. We hope to hold a roadmap consultation workshop in early to mid-June 2025. And leading on from that, as you see, there'll be other events. In particular, maybe also alongside the roadmap consultation will be an industry engagement workshop as well. So we may bring those two together. But there'll be other roadmaps in terms of the development, the review, and the production of a white paper. We also hope to offer sandpit workshops early in 2026, where small kick-off projects may be funded, so there may be some funding opportunities in there as well. And later in the grant, also some grant writing retreats to look at larger scale proposals for future research. And we hope to meet as a group bi-monthly as an absolute minimum in terms of the management committee. So please keep an eye on the network's website for the dates for these activities. Sign up to our particular group if you're interested in being involved in these activities, and we'll endeavour to let you know exactly what's happening as soon as we can and when it's happening. Okay, I think that's all from me from now, Ziwei. So thank you very much, everyone, again for attending. And I'll hand over to Ziwei for
Okay, thank you. Yeah, thank you very much, Mike. So as you can see in our agenda, we're going to have two sessions. One is more oriented to human factors. The other one is on machine intelligence and human-robot interaction. So first of all, I'm very honored to have Professor Fernando Biana here. He's the professor of medical robotics in Department of Mechanical Engineering at Imperial College, where he leads the mechatronics in medicine lab and the applied mechanics division. He's also the co-director of Harmony Center at Imperial College. So I'm very happy to have Fernando here, and with his supervision and support, I learned a lot in medical robotics and Da Vinci robotic systems. So now it's your time to give our presentation, Ferdy. You can now share your screen.
That's it. Can you see the slides?
Yeah.
And can you see me? And can you hear me? So the sort of three important things before we go any further. Let me just, I want to move, that's it. Now move it here. Now, I could also ask if anybody wishes to to show me their, no, this is not, just 1 second. Let me just, I want to see people. It's always difficult to present without, here we go, without anybody in front of you. I mean, we've all done it through many months of COVID, and then you forget, and then you start again. So it's great to see the event. Sort of Ziwei, thank you very much for inviting me. It's a pleasure to be here, and amazing to hear about this new initiative. So best of luck with ACE. I am pretty sure it's going to be a great success. So Ziwei asked me to give a short overview of some of the work we do in surgical robotics and machine learning within the Hamlin Center. So I'll specifically focus on that in this sort of 20 minutes or so. And to start with, I think it's important to say that robotics at Imperial, and especially healthcare robotics, is a major aspect of what we do. There's a number of academics across the Faculty of Engineering that do all sorts of robotics, whether it's in surgery, working with children with a disability, working with stroke patients, human augmentation, and the like. And the work of the Hamlin Center focuses predominantly, but not exclusively, on the bottom right-hand corner of this area, certainly with the work that I do in first person on surgical robotics. However, right, our mission is to really sort of work across imaging, sensing, and robotics around healthcare as a whole. And we have made some strategic recruitment in this topic area to make sure that surgery is not the only focus for the work we do in the center. And in fact, I'm delighted to have Liu Ma, one of the latest acquisition, a young academic with a background in healthcare textiles, who joined us in January, and she'll open the research focus of the Hamlin Center to hold a whole different set of challenges. Now, within the Hamlin Center, there's 9 full-time academics, as you can see, that cover broadly robotics, imaging, and sensing. And in this particular academic setup, George and myself specifically look at surgical robotics. And so it is quite fitting that over the next 15 to 20 minutes, I'll be focusing specifically on what I do as part of the Hamlin Center within surgical robotics. Now, within that center, I run my own lab. It's called Mechatronics in Medicine. It's been around for a long time, and it tends to focus on hardware, right, for surgery, smart hardware. So let's say robotics. Now, the difference between giving the presentation now and a few years back is that there is indeed a whole lot more machine learning and human-robot interaction now than there was in the past. And that is thanks to the many advances that we have made collectively in this topic area. So now, if you look at the space of surgical robotics today, it is very different from what it was 20 years ago. You see a number of major robotic systems that are endowed by a corporation that has the money and might to be able to support it in the long term. And this is not has not always been the case. Robotics were, so the surgical robotic systems were sparse and usually came out of a university endeavor through a spin-out company and so on. And many of them fell by the wayside in the past sort of 20 years or so. But what you see on screen are robots that have actually managed to sustain themselves and remain alive for long enough to be acquired. And so Mazor, who's an Israeli company, is now part of Medtronic. You've got the Mako system that came out of Silicon Valley, who was purchased by Stryker. You've got, of course, the One Might robotic company called Intuitive Surgical, and there are others popping up here and there. And of course, we have our own, and that's why I start with the past, we have our own experience of surgical robots that made it all the way from bed to bedside with the incredibly ugly, with the incredibly ugly robot you see on screen. It was called the Acrobot, and it made it into an operating theater working on patients in the early 2000s. Now, although it was ugly, it was the very first system in the world that did this type of robotic machining of bone, which is cooperative. So it's not the robot working alone or the surgeon working alone, but it's the surgeon holding the robot, machining the bone cooperatively. And in the early 2000s, that particular system was very innovative. Now, clearly it is not anymore because things have progressed enormously. I mean, my PhD was on the registration aspects of the system back in the early 2000s. And I think it took several minutes on an incredibly beefy processor to do what you can now do in milliseconds on your box standard mobile phone. So clearly it's a different age, but it is surprising that regardless of how far away this technology was back in the 2000s, how little a difference we have made on the commercial systems out today. And so the reason for the lack of widespread adoption of some of these systems in the broader sense are multiple. Some have to do with hospitals and workflows and patients and cost effectiveness, and some are technological. And I think from this point, you'd probably be able to spin out two completely complementary lectures, one focused on the clinical reasoning behind why robots haven't quite made it to the mainstream, and some are technical. But given the audience and given my technical background, we will focus on the technical by looking at what have been the three main areas of development that have continued to take center stage in my own research group in an attempt to make these robots a little bit more mainstream. And for me, and this is a very personal thing, the three technical stumbling blocks that basically separate us from these robots becoming a little bit more ubiquitous have to do with smoother interactions, automatic recognition, and smart devices. What do I mean? I mean, systems need to be better suited at working within the workflow of surgery, and clearly they have to be able to work on their specific sub-aspect of a task without the clinician, the surgeon or surgical staff having to do anything different from what they're doing in the conventional workflow of that surgery. And that is easier said than done. Now, within this context, we have worked on each one of these three and are continuing to work on each one of these three main topics. And they've all been enhanced dramatically by the advent of deep learning networks and machine learning, which have really sort of changed the landscape of what we can do today. So what you see here is a bit of work that's a little bit dated now, had to do with cooperative control, this idea of shared control between surgeon and robot, which back in the days of Acrobot had to forcibly be limited to working with static, rigid targets like bone. But of course, we would like it to work equally as well in the soft world of dynamic targets like the general, sort of like general surgery, like working on the prostate, the liver, vessels, and so on. And so back in 2015, we started to explore how could you take this idea of cooperative control and apply it to dynamic, moving, soft things, which of course raises the bar of complexity by quite a bit. And over the past few years, and this takes us to the work that Ziwei was part of before he moved and became an academic, which has to do with taking this idea of cooperation all the way to a step where instead of just supporting the surgeon, you're actually taking away some aspect of surgery and automating them entirely. So what you see here is the first bit of work that I wanted to share, which has to do with cooperative. So here, robot and surgeon are working together, but on soft and dynamic tissues. So they're basically the state of the art, something that exists within research groups and in laboratories, but hasn't quite made it all the way to the operating theater. So here you've got the Da Vinci surgical system, and then a depth camera that is acquiring information about the tissue so that you can constrain the operation of the surgeon who's working with the robot, but on the fly as the tissues are deformable. And what you see here is some first attempt at doing this using a silicon phantom, which shows you the steps forward in being able to avoid the tool intersecting or inadvertently damaging, in this case, a phantom of the vascular structure. But of course, it also shows you the limitations of where we're now, with the delays and the lack of accuracy, both of which are integral to our ability to eventually place this within an operating theater. And now more specifically for Ziwei, we actually took the idea that the surgical system that Intuitive Surgical produces has more than two arms. And so there is this idea that with the right control strategy and the right learning paradigms, you can actually take one of those three arms and get it to do something that complements what the surgeon is driving directly through the left and the right hand. And this is some very, very early work of peg transfer, where one arm is actually controlled by the surgeon, but the other one is controlled autonomously using this deep learning approach that infers the expectation that the surgeon has. Now, clearly, this is very foundational, very early work, but it at least gives us a hint of what a future of tomorrow might look like. So not one that just works to either guide or constrain the movement of the surgeon, but one that can actually almost act as an assistant to surgery to make procedures that were inoperable, operable, or pushing the bounds of what the surgeon can do. Now, on a similar note, if you look at every single commercial system to date, there are these two things that are shocking, but exist in industry today. And that is the fact that for all intents and purposes, as of today, we use 1980s technology, or in fact, flat screen came out in the 1990s, maybe. So basically a 2D screen to represent three-dimensional information. So this screen, and two, for any complicated mapping of patient and tissue targets, you use percutaneous fixations, which for those who are not familiar with the nomenclature means sticking pins directly into the bone with markers that you can then use to track where the bone has gone during surgery. And these two aspects are, for me, a very limiting factor to how broadly you can make this robotic system available, because they very much break the way that workflows happen in surgery if you weren't to use a robot. So what have we done in this context? Well, on the visualization point of view, my absolute belief is certainly that augmented reality will eventually make it into the mainstream. And that is where you take information from your plan or from your guidance cues, and you overlay them directly within the eyesight of the surgeon through some sort of headset. This is early work we did with the HoloLens, where you can see here, you actually have guidance cues that are overlaid on the view of the surgeon, as opposed to being only visible on the screen on the right. And if I show you the next set of videos, we have done this within a cadaveric setup where you're literally looking at the exposed patient on the operating table and can infer what you must do, in this case with a robotic system manufactured by Smith & Nephew, on the patient without ever having to lose track of what you're looking at by triangulating what you see on a screen off-site and then back onto the patient. And of course, the next thing you have to do is to find a way for the system to know where the patient is. And that is not straightforward if you take these pins that are very invasive out of the equation. What we have done over the past few years is using depth cameras, your classical Kinect, right? So your Xbox Kinect, which basically not only acquires red, green, and blue information from the scene, but it also acquires depth information in the form of a point cloud. And so again, through a whole lot of labeling, a whole lot of training, and a suitably engineered deep neural network, we were able to teach a system endowed with a depth camera to infer, as you saw in this video, what is bone from what is not bone. And that is generalizable to any camera, generalizable to any phantom or tissue that the camera had never seen. And it is also occlusion resistant, as you saw on the bottom of the screen. And once again, we embedded this additional intelligence, in inverted commas, within a surgical navigation system from Smith & Nephew, where you can see here on the screen a cadaveric trial where red represents the proximal side of the leg, so the femur, and green is the tibia, and they are tracked in real time without any markers or any previous knowledge of the anatomy of that bone. And of course, that gives you an idea of, at a point in the future where both the identification and the tracking of the limb happens without any surgical input. And then, of course, all the information you need to operate comes through a headset. Clearly, there is software and then there is hardware. And on the hardware side, we still have a long way to go in terms of making robotic systems easier to integrate within the cluttered environment of an operating theater. And here in the screen, you'll see some work that we're doing on soft robotics, which is certainly one of the most topical areas in surgical robotics at the moment, where we're using this idea of everting, they're called vine structures, to create soft robotic manipulators that find a way through your lower GI, so basically through your intestine, to identify small lesions or, for diagnostic purposes, deep within your intestinal tract. And so once we've got that system in place, we can then use bimanual operations, which is what you see here, or non-contact diagnostics, which is what you see in the bottom left, to identify what's wrong with the patient and then act upon the lesion right then and there without having to go for a second procedure. And on a similar note, to close things off, this is my third child. This is a very large program that has lasted over a decade in the mechatronics and medicine laboratory, where we're looking again at soft robotics but for needle steering. It is called Eden 2020 in its latest embodiment, and it is basically a biologically inspired needle steering system for deep lesions in the brain. Now, what you can see in this animation, which is unique, is that the needle is not one, but is 4 interlock segments that move relative to one another. And this allows us to do a couple of things. It allows us to deliver optics and tools deep within the brain, and it allows us to curve around the brain without having to either twist or push, which in turn makes this safe for use within the very delicate neural structures. Now, clearly, once you are where you need to be, you can do multiple things. You can do laser ablation. For example, if you had a lesion you want to get out. One of the major areas we looked at is drug delivery. It's called convection enhanced delivery. So basically the gentle flow of chemotherapeutics directly in the lesion, bypassing the very complicated blood-brain barrier. And then very topical at the moment is a whole world of work on diagnostics and therapy for neurodegenerative diseases like Alzheimer's and the like. Now, the system, it looks indeed like the animation, so I just wanted to put it up on screen. And at the moment is in this sort of uncanny valley where it either flies as a commercial venture or dies the slow, painful death of technologies that don't quite make it for one reason or the other. And if I were to put my heart in front, I would say will fly. If I were to put my brain, I am not so sure, because it's a very complicated system in a very niche market. This said, I think the jury is still out to know for sure exactly what happens with this technology. So to conclude, I would say that for the audience of this seminar, the area of surgical robotics, machine learning, and AI for health has never been more fertile. It is an incredible, I'd say, theme park for the right person in the right area. And so you're encouraged to explore this particular topic as a potential future avenue for your research if you are not in that field already. With that, just to close, thanking all of the people that obviously work within the center and the research group and all the funders that make it possible. And a reminder that we do run a yearly symposium. This is usually the last week of June. And for those interested in medical robotics and allied technologies, it is an incredibly great opportunity for a local conference at a fairly moderate price in the UK to hear some of the very best people coming from all over the world for that occasion. Dates are there, and call for papers will close in the next week or two. With that, thank you very much for your time. And of course, I'm very happy to take questions. Zeyu, do it.
Thank you very much, Freddie. I'm quite impressed by a lot of advances of Hamlin Center, and I think these technologies Hamlin have already achieved will definitely help a lot of advances in the other sectors. So I will just wait for several minutes to see if there's any questions to discuss from our audiences. You can just shout out or leave your message in the chat.
Stand into silence.
Okay, so I have a quick question about the application of large language model. As everybody knows, we've seen a lot of applications of large language models such as GPT or DeepSeek recently. So I'm wondering if these large language models will have the great potential to be used in the medical robotics. How do you think of these?
I mean, 100% yes, right? So I very recently wrote network class grant that unfortunately was not funded because of, and it was all based around this idea of using large language models effectively within the healthcare domain. And I think the low-hanging fruit is as a parser, right? So of course, we all know that large language model can hallucinate and they're not always accurate. And so, of course, the last word is always with the expert, whether that is the clinician or whether it's the patient, if it's something to do with the patient. But I think the real value in the short term, the large language models and GPTs have in our sector is to help us basically sieve through the enormity of problems and potential solutions that exist already and that remain unanswered, to identify some aspect that requires the attention of a selected few, right? So I have this sort of vision of, a community that is sort of supported by GPTs, right? That helps you to identify like-minded people where you either have the same problem or you have problems and solutions. And I think in that context, the algorithmic evolution of all of this is already ready, right? Because it doesn't need to be perfect. And that's just the beginning. We're seeing, month on month, the progression of these technologies. So I think it's almost impossible to even imagine how far we will be in 5 or 6 years' time. But the quick answer is academics talk a lot, but the quick answer is absolutely yes.
Yeah. So I absolutely agree with you. We have one question from the chat that the question is, how do advances in AI and robotics integration address the changes of precision of adaptation in medical robotics, particularly when performing catheter placement?
So catheter placement, I think, is almost an optional bit of the entire question because I think it applies across the board. The short answer is not enough. The potential is huge because, of course, medical robots and navigation systems tend to be the dumbest of the lot, right? Because you always prioritize safety over efficacy and smartness because you're always conservative in surgery. But of course, there is a huge opportunity in the space of surgery, which remains more of an art than a science, because there is a great capacity for these algorithms to learn how best things should be done and to make things that are more bespoke to the patient that you've got in front of you. We haven't even scratched the surface of that world of opportunity because at the moment, machines tend to be very, behave the same way predictably using the same protocols. And I think the legal framework that allows you to push the boundary is slowly catching up. But the real value that would be enabled by machine learning in this context would be, for example, for that catheter to be supported. So to the delivery of a catheter with navigation or robotics by a surgeon could be supported with a lot more quantitative information about how you'd plan for that procedure for that particular patient based on the specific need or preference of the clinician that is doing the surgery. That has not happened. It certainly can happen. It's just a question of getting all the bits together at the same time and making sure that the legal framework to do it catches up.
Okay, thank you very much for sharing your thoughts on these points. And we have to move on for the second speaker. Thank you very much again.
It was a pleasure, Ziwei.
Thank you very much
again, and for everybody, thank you for inviting me. Enjoy.
Thank you, Freddie. Okay, so after that, we are going to have the second speaker, who is Pei Huang. She's the lecturer at the Department of Engineering and Design at University of Sussex. So before she joined Sussex, we worked together at the Department of Bioengineering, Imperial College together for like 2 years or so. And we did a lot of works on human-robot interaction and teleoperation. So I'm very happy to have Yanpei here. So Yanpei, can you hear me? And you can share your screen.
Yeah, thank you, Zui, for the introduction. I'm going to share my screen. Okay. Okay, are you able to see my screen? Okay. Hello everyone. I'm Yanpei Huang. I'm very happy to join this ECR webinar on the control technique in human-machine intelligence. And I would like to share about my research on movement augmentation for robot-assisted surgery. As we have already introduced me, please allow me to introduce again briefly. So I was born and grew up in China, and after that I had my master and PhD at Nanyang Technological University in Singapore, and then I joined Imperial College as a postdoc researcher. I worked there for about 3 years. I'm mainly working on EU project, collaborate with Freiburg University and Sorbonne University, working on human movement augmentation. And after that, in 2023, I joined University of Sussex, working as a lecturer. So my research is mainly on augmenting human capability with robotic assistance, and especially his translation towards surgical systems. So it's a quite interesting topic, kind of how do we enable human to become superhuman to do the tasks they cannot normally do use their normal hands. So this includes developing intuitive and efficient human-machine interface and human-robot shared control and autonomous robotic assistance. So we have all known that robotic surgery is increasingly used in hospitals, and many of the robotic systems are teleoperation systems with master and slave devices. So this figure shows, so when using this kind of robotic systems, the surgeon sitting behind a master console to control the remote robotic systems at the patient side. So this figure is illustrated the endoscopic surgical robotic system at NTU. We can see from it, except the main surgeon, there is one endoscopist standing at the patient side to help the surgeon to adjust the view and control the endoscope. So the collaboration between the surgeon and the endoscopist is very important for the final performance of the surgery. But we have found that there are some communication issues in the operation room, and it is a primary point of vulnerability for patient safety and efficiency. There are also data from the WHO guideline for safer surgery stated that 70% of the adverse events in the operation room are due to communication errors. But we know that there are many surgical scenarios require close cooperation between surgeon and their assistants. So this slide illustrated some surgical tasks in robotic surgery involve more than 2 instruments. So the assistants may help the surgeon to control the laparoscopic camera or flexible endoscope to provide the view and load the instrument to target area. Or the assistants may control the suction tool to suction the blood and help the surgeon to clear the view to conduct cutting or suturing. Or the assistant may also help in the laparoscopic prostatectomy to control the robotic gripper, to elevate prostate base to create tension for surgeon to perform dissection, or in laparoscopic hysterectomy, the system needs to grasp and lift the tissue while the surgeon performs cutting. So we can see that there are so many tasks require close collaboration between surgeon and their assistant. Then how do we solve these communication issues? So one idea is we can augment surgeons' ability to enable one surgeon to control multiple surgical instruments all by themselves. So it's kind of enable the surgeon to have a third hand to control the additional instrument and replacing the human assistant. So this can be achieved using the hand-free interfaces, use the other body parts of the surgeon to control the additional surgical tools. So there are many possible body parts can be used to acting as the third hand to control the additional surgical tool, as illustrated in this figure. So it could be eye gaze, it could be head movement, finger movement, foot movement. So there are already some research working on the eye gaze control, use the eye tracker to control the gaze data of the operator and use the data to control the laparoscopic camera. There are also systems using the voice command, so the surgeon will wear a headset and they can use some simple voice command like moving forward, left to control the laparoscope camera. There are also systems using the head movement, so the surgeon will wear a variable sensor on their head to sense the movement and orientation of their head. And this signal will be used to control the movement of laparoscope. There are also systems using the finger or foot interface to control the laparoscopic camera or flexible endoscope. So it's also possible to using other body parts like muscles or brains like EEG or EMG signals to control the additional third instrument. So next, I would like to share about my work on development of a hand-free foot interface to control a robotic endoscope. So to control the robotic endoscope, the endoscope normally can be used in the endoscopic surgery to move in 4-degree freedom to load the endoscopic tools to the target area. So we to consider this application, we want to choose proper foot gestures to control this endoscope. So we're considering the foot human lower limb biomechanics, also considering whether the gestures can introduce more human fatigue or whether it's easy to operate. So based on that, we have choose 4-degree freedom foot gestures to control this flexible endoscope. And the idea to collect all those foot gestures is locate multiple feedback and sensing modules around the foot to collect and assist the natural foot motions. And each feedback and sensing modules is including serial connected spring and load cells. So we locate 8 sets of feedback sensing modules around the foot. And we also use a parallel or serial structure because this structure can provide compact mechanisms. And based on this structure, we have the 3D design of the systems. So we can see from the figure that so the feedback and sensing modules, including the elastic element, which can provide dynamic haptic feedback to the user. It can also provide automatic homing position. So when the user finish the operation and release the pedal will automatically stay at the middle position, providing a resting posture for the user. And the load cell will collect a force signal from the operator. And even in the boundary of the workspace, the user can still exert force. So this avoid the ceiling effect of the sensing of the interface. So here is a illustration of the movement of the interface. It's allow the 4-degree freedom motion control. So the movement not only in the single Cartesian directions, it can also move in diagonal directions, combine multiple degree freedom. So it can provide natural and intuitive control. So the development of the hand-free foot interface is just the first step of human augmentation. So we still have many questions need to answer. For example, is it possible to control the third tool hand-free? Can one person control 3 or more tools together? And is there different operation to manual strategies in different tasks? And what the effect has third hand control on the natural behaviors? And how do humans learn to manual operations? And how to efficiently train to manual solo to manual operation after perform diet operations? So to answer all those questions, we need systematically experimental studies. So I would like to share some of our studies to answer those questions. So first, we perform evaluation studies to check, is it possible to control a robotic arm using this proposed foot interface? So we can see from this video, we built a teleoperation system to enable this foot interface to control a robotic arm to perform some accurate task. The task is actually very challenging, even for the hand operations. The operator need to use their foot to control this robotic end effector to follow this weird trajectory. And they can use the interface to, we can see that after some trainings, the user can easily control the movement of the end effector and don't touch the mantle wear. So after this test, we also perform another study to evaluate whether this proposed hand-free interface can be used to control a surgical tool like flexible endoscope. And this video has illustrated the mapping between the foot motion and the movement of the remote endoscope. We can see that the mapping is very straightforward. The operator can just imagine his foot is the tip of the flexible endoscope and provide corresponding motion control. And we have also compared this foot teleoperation with hand teleoperation and conventional direct manual control. And the result is showing that this proposed foot teleoperation have similar performance and even better performance than the conventional manual control, but it's still a little bit slower than the hand teleoperation. But we know that the user can be trained and studied this third hand control. After that, we perform another manual study to check whether one person can control 3 or more tools together in a surgical task. So we perform a EX-Vivo surgical test with a 3-limb teleoperated robotic system for endoscopic surgery. So this video is illustrated. One operator is operating the whole systems. The whole systems can provide totally 13-degree freedom control on 3 surgical tools. So the user is using their left hand, hold the hand controller to control this robotic grasper. And the grasper is lifting the tissue, and the right hand is control this cattle riding hook to cutting at this target marked area. And the user is using the foot interface to control this black flexible endoscope to load the instrument to the target area and also adjust the viewpoint. So we have proved that using this experiment that one person can control 3 surgical tasks together to perform this solo surgery. We also have some other testing videos with this hand-free interface to control supernumerary robotic limb and cooperate with natural limbs to perform a task with 3 object reaching task. And there are also demonstration using this interface to control orientations of this target tube, while the 2 robotic arms grasping the object. There are also another demo with the famous Da Vinci robotic systems. The interface, the foot interface is controlling a 3rd laparoscopic instrument together with the other 2 hand-controlled instruments. We can see from the video that the foot controlled instrument is changed orientation to facilitate the control of the hand controlled laparoscopic tools. This is my last slide. Finally, I would like to share about some information about the new build center at University of Sussex. So we built a new center for robotics and sensing technologies, and we currently have 13 PIs working on various fields in robotics technologies, including soft robotics and technology, high precision robotics and sensing, unmanned vehicles, and automation and interaction robot. Please feel free to contact us if you're interested for any collaborations. Okay. Thank you everyone for your listening. I'm happy to take questions.
Okay, so any questions from the audiences? Because this time I've known a lot of Yan-Pei's work, so maybe I have no questions about her presentation. Okay, so Lan, you are free to ask any question.
I just raised my hand to ask a question. Yep, so I'm going to double check whether I turn on my microphone. I think everyone can hear. Yeah, so thank you very much for your presentation. I want to ask a technical question. The technical question that is when you saw a video demonstrating the control of the endoscopics. To my knowledge, I think it is a quite challenging work, especially when the endoscopic that is at a steady state, and then during the steady state, always there will be some vibration. So do you have any comment or some ideas how to suppress this kind of vibration?
There will be some vibration. You mean control the endoscope?
Yep.
So
yeah. So
yeah. This is a real this is a real problem in the operation room. So currently, we develop robotic endoscope systems. They're actually a holder, moving together to hold this flexible endoscope. So only the tip part is moving, and after that, there will be a holder to holding this part to remove the vibration. But as you said, there's still some problem on the vibrating, the small vibrations, even we have the robotic holder.
Right. So that means from the control point of view, what I want to say is that whether it is possible, for example, to develop some more smart control theories so that it is possible to suppress this vibration instead of using, say, some hardware support or something like this.
Yeah, I think it is possible if this vibration, if we test a vibration in advance, and if we can find some patterns of those vibration, and in the hardware and control part, we probably can provide some algorithm to compensate these vibrations in advance using algorithms.
Right, I see. Okay, thank you.
Okay, so any other questions? All right. If no questions, let's just move on to the industry session, which is also the panel discussion. So besides the academia, in a lot of universities in the UK, we also warmly welcome the industry to be involved in our theme as well as ACE network. So today we have two members from Acquiring Minds and one from J4IC, which is a sector of TWI. So I would like to introduce a bit before we have the real session. Okay, so as we know, so TWI is the famous worldwide company in terms of the welding technology and etc. And Acquiring Minds is the deep tech UK company which since 2010 has been successfully deploying AI solutions in smart cities, healthcare, industry, and a lot of sectors. So it's really great to have both sides here. And today we have Nick a lot and actually Setter from Inquiring. And we are happy to have Dr. Hao Linfei at J4IC to be involved in this session. Okay, so great. I've already seen your faces. It's been a long time since we finished the Innovate UK project. I'm 3D Pro after, so it's great to say hi to you. So since then we've already had learned a lot from the previous speakers about medical robotics, human-robot interaction, and etc., which are very impressive. But now we are at the stage to think of some questions for you and also for the audiences. So the first one is, how do you think about the frontiers of medical robotics from your perspective? Because as you can see, the videos from Yanpei and Ferdy, that a lot of robotics technologies can be used in different sectors and different applications. So how do you think about the potential of these medical robotic techniques and where the next frontiers will be?
Do you want me to try and start?
Okay, no problem.
Sure. So maybe I'll start by giving a bit of context in terms of where we're coming from. So as a company, we specialize in practical applications of AI, and we specialize in sort of like data fusion from different sources. It's a broad sort of capability. And in almost everywhere we deploy, you can characterize it as a control system. It's always a feedback loop. We start with our data inputs. Some are high velocity, some are low velocity. There's always a level of modeling. There's a decision space where we choose to act. And then there's the control loop, where we go back to where we start and then we start with inputs again. So therein lies the control loop. What changes is the speed at which it works, and it shifts from sort of like from application to application. So on the one side, where we've got experience on the industrial side, it's super high velocity. You're talking like control loops of milliseconds or microseconds in terms of turning. In terms of your like problem space, in terms of aging society, we don't have any direct experience of robotics. We do have direct experience of 4 areas of health related to social care. So maybe if I talk through those, and that will give you a sense of where the problems are. So the first is classic sensor deployments for social care. And it's a classic pattern of life problem, right? You're taking data sources from someone in their own home, you're fusing them together, and essentially you're detecting anomaly. But then you need to detect anomaly with the right false positive characteristics. Otherwise, you can't deploy it. It's a purely academic construct. And the reason is a false positive, right? It is extremely expensive because it means you deploy someone to someone's home when it's not necessary, and the state can't afford that. And a false negative can be disastrous because it ends in death. So it's a control loop. It's a slow one. It's not a micro millisecond one. It's measured in terms of like minutes and hours. And I thought this is wrong. The decision space of the false positive and false negative is super mission critical. And there are so many ethical considerations around that. That often is the fundamental biggest problem with deployment of any health technology. The science is great, the innovation is fantastic, but the operational risks of deployment are cataclysmic. And because of that, there's a lot of processes and procedures and certifications, etc., that essentially produce a massive amount of necessary friction on commercial deployment. So that's the sort of like the social care sensor one. I'll touch on sort of like two others that are, but also control loops. They're slower, right? And these are the control loops of, you know, you look at patients, incoming patients with their needs, and you prescribe them a package, right? In the social care construct, that can be a 2-year feedback loop. Surprisingly, because at the point at which that decision is made to deploy the package, because of the way subcontracting works, and people often don't know what the end result or how effective that package is, comes down to sort of like restrictions in states. But again, you know, the decision space is really hard, because the decision space is essentially a resource allocation problem. So when you look at the problem, you know, and we've been given access to some of this data, which is highly confidential. You'll have people on packages that can cost upwards of £500,000. You have other people on packages that can cost like a couple of £100 a week. How do you ethically decide where you distribute your resources within that context? It's almost an impossible ethical problem. It is a control loop problem, because every time you do it, there's a feedback loop in terms of, well, how long did they live and what's their quality of life, etc. So you can characterize mathematically using a number of different parameters, but how do you actually decide that? Well, it's almost impossible, and we essentially excluded ourselves from that, and all we do is present the data in the best form possible. And I'll just talk about a third one. It's quite a long way from your robotics area, but it's still a control loop problem in the area of aging, and that's to do with workforce and workforce deployment. It's completely different to package allocation, but it's also one of the critical factors in terms of whether we looked at workforce actually more in the healthcare context rather than the social care context. It's an extremely slow control loop, because the speed at which you train GPs and deploy them fundamentally affects the capacity of the system. And if the capacity of the system, you know, clogs up because you're not sending people to the right correctly qualified professional at the right time, you know, you either are over-resourcing the problem or you're under-resourcing the problem. So again, these are really complicated ethical problems with a lot of sort of technical complexity under the hood. But it's a very long way of answering your question. It is, yeah, there are major technical challenges, but I'd say from a commercial perspective, your major impediment is understanding the process and the procedures and the ethical constraints in which it needs to be commercially deployed, and frankly can be in many cases totally crippling.
Yeah, thank you a lot for your thoughts, and thanks for raising the ethical consideration for the users. So I would like to know if you have the similar ideas, Howling and Dash.
Okay, just thanks so much, Nick, for your view. Long time no see, and I'd like to add that based on the point you just talked about, actually, if we have the whole system, like we have all these technical issues solved, I think there's even more challenges that we usually don't think about at the even at the very late stage of the project, which is the user trust and the adoption. So actually it's two parts. So for medical robots, it's for the user can be the clinician and also the patient. So that, well, for example, I just lately happened to see an experiment that they actually solved all these technical issues, and they are already doing experiments in the hospital. But the thing that although this system is fully, I mean, it's well tested, and the trust is one of the things that we definitely need to think about, because for the guys who develop the systems, they have faith in the whole system. They know how it works, but for patients, they have very low trust in the whole system. And also, one of the things that we must think about is the transparency of, for example, if they are using AI AI technology, like for that example, they're actually using view serving to first recognize and locate the face, and then use depth cameras to estimate the user's position, the gestures, and then use the algorithms to drive the robot to the exact location to do the following procedures. But the transparency of these AI decisions are actually something that we definitely need to think about, because for patients, they don't actually care so much about the precision, especially for those experiments that actually approved, because most of them are not those very dangerous tasks, right? For these tasks, they actually need some support, like also the transparency from the, doesn't matter it's the clinician or the AI systems. They want some information from that, and also we need to also think about the emotion support. Like they can, if it's a human clinician, they can actually talk, they can communicate during the whole procedure. So that's actually something that we need to think about, other than the not just the safety, but also the users' trust and adoption.
Okay. Thanks for sharing, Howdy. Yeah. So what do you think about this, Ash?
Yeah, I think, to be honest, Nick and Howlin have covered it all off very well, actually, very succinctly. I don't really have anything much to add, to be honest.
Oh, all right, no worries. Okay, yeah. So as we can see, we like to have the very successful enterprise, like the TWI, or what inquiring minds have already achieved. So how do you think we can realize the transfer from the lab to the practice? It's a kind of the question about the entrepreneurship in automation. So we would like to see some shortcuts to commercialization. Do you have some ideas to motivate the some possible successful companies in the future?
I mean, to some extent, it's replaying what we discussed before. It's all about risk management, but the risk management is there for good reasons.
Yeah.
I mean, maybe to try and collapse it, I think there's three critical phases that need to be considered. So the first is just the technical efficacy, right? Doesn't matter what the system is, whether it's a surgical system, whether it's a monitoring system, whether it's a diagnostic system. You need really, really strong data on does it work and what is its error rate. And you know, error rate is a much more nuanced and complicated thing. But I think the false positive, false negative is one construct in which that's well understood, and that gives you your technical foundation. And that needs to be watertight and externally verified, because certainly from a commercial perspective, you know, the vendor is not trusted to mark his own homework. So that's the first level. The second level, and this is probably one of the trickiest when it comes to health, is understanding where your solution fits in the clinical pathway. And there are a lot of medical innovations I have seen and my colleagues have seen where it's quite clear the innovator, they understand the technical problem, but they don't understand practically where it's used. I mean, for example, there's a massive difference between an NHS clinical pathway and a private clinical pathway, and then there's a massive difference between sort of inpatient, outpatient, and I mean, it becomes very, very nuanced and very specific down to the specific condition that you're managing. But you really need to understand the mechanics and the economics of that clinical pathway in its entirety to know whether you have a viable proposition. And I think that then the third layer that I've already mentioned, but hopefully it's covered up by the checks and balances, is that a lot of the innovations we're talking about do raise quite considerable ethical considerations, and that risk needs to be sort of like measured off. But so yeah, so to your question, how do you accelerate progression from sort of like lab to market? It's about efficient risk management, because you can just say risk management and then let's turn the dial up to maximum, but then nothing happens. I mean, that's why everything gets stuck in the lab. So those risks and those risk levels that I talked about need to be managed in a complete way. But you also need to think of it at a system level, because there is a risk of doing nothing. Because for some of these innovations we're talking about productivity increases, and without the productivity increases, you have a fractured and a non-functional system. So there is a risk of doing nothing. It's not always the least risk thing to sort of like minimize innovation. So hopefully that helps clarify a little bit where we see the issues.
Yeah, that's quite helpful, and maybe we can start from learning from industry, well, to do some collaborative projects with the industry sectors to learn the real needs from the market. Yeah, okay. So any top up from Howling and Ash?
Yeah, I mean, I totally agree with Nick. So that because industry cannot innovate in a vacuum, right? We need to open dialogue between with clinicians, so that we can have real unmet needs from their perspective, and also we need the academia to address to solve foundational technical issues like the creating robots that can adapt to surgeon's style. So in conclusion, that we actually need we need to open dialogue with both clinicians and academia. And the first stage, I believe, is to identify the unmet needs, so that the industry and the academia can then work, and then this can form from system level a closed loop.
Okay. Yeah. So Ash?
Yeah, I mean, I think I agree with all those points entirely. I think the other thing to consider is that commercial organizations and organizations like the NHS and the places where these technologies will actually be deployed tend to be very slow moving. So it's difficult. It's best to engage them as early as possible in the project and sort of get them involved as you go along, because it's quite common to sort of, focus on your technology, really make something innovative over, a course of years even, and then you come to talk to the people that actually want to, where you actually want to deploy it, and then that process is then years again on top of the time that you've taken to actually innovate on the product itself, the technology. Whereas if you can engage them earlier on in that process, you can sort of get the ball rolling and get the wheels spinning that need to be, the processes that need to happening as early as possible, so that there's a shorter time between the product being, or the technology being ready to use in some form and actually being able to be deployed.
Okay, yeah. Thank you very much for coming and sharing your thoughts on these topics. Thank you very much. Okay, so we're gonna have several times break, and we'll have the second session at 3:25, and the topics will be still very amazing, involving machine intelligence, human robot interaction. We're gonna have Dr. Lam at King's College and Dr. Wei Yongsi from the Uni of Essex, and we're gonna have the industry and poster showcase sessions in the following. So I'm gonna grab a coffee and come back at 3:25. See you guys later. Hi everyone. Just a short break, and I'd like to introduce the first speaker of the session 2, who is Dr. Lam at King's College. So Lam is the reader in computational intelligence at King's College London. His current research interests include intelligent control systems, computational intelligence, and machine learning. He's an IEEE fellow. He was named as highly cited researcher since 2018, extract from Web of Science. So I believe Lam will talk about more in the topic of machine intelligence. So his topic will be understanding AI models using fuzzy logic. Okay, so welcome to our webinar, Lam. So yeah, it's your time. Lam, you are muted.
Yes, I'm checking whether I'm muted or not. Yeah, so
Okay.
yeah, so I hope everyone can see the screen as well as can hear me. And thank you, Jiwei, very much for introducing me. So today's topic that is a little bit different from what you just mentioned, but along the same line. Yep. So the topic today that is about explainable AI and some potential application for aging populations. So my name is Haekang Lam from Department of Engineering, King's College London. So it is my great pleasure today to give a presentation about that. I also like to thank my students, Yuhan Wang, Falan Yan, as well as Fang Zheng. They're here for today's presentation. To support today's activities, as well as Fang is going to give a video presentation later on about the reinforcement learning for the control applications. So today, because I only have 20 minutes, I'm going to make everything at a high level, and then I try to provide some ideas about how do we integrate some application, especially I'm talking about the fall detection or prediction, this kind of application using the black box approach or the machine learning approach, and then how do we use the explainable AI to improve the user trust. So that is something, some concern we have discussed during the industrial session. Okay, so today's outline, that is basically we will talk about these kind of things. As I mentioned, that this topic that is about the aging population. So I'm going to give a little bit ideas about the challenges we are facing in the aging population, and then mainly I will, because when we talk about the challenges, there would be a lot of challenges for the aging population. I will just focus on the fall detection or the fall among the old adults, and then the idea that is not limited to the fall application. It is possible to extend to many other related application. Okay, and then I will give a little bit more ideas. How do we combine the explainable AI as well as this kind of this kind of application, and then to give us a better idea what would be the explainable AI and how they relate to the four application. I will talk a little bit more about some particular scenarios. That means I'm not able to cover everything within 20 minutes, but I try to make things simple to get everyone some ideas what actually it is, and then later on some potential applications for the explainable AI. Okay, so this is the challenges of the aging population, and then according to the statistic, to my knowledge, we have 68 million people in the UK, and then 90% of in the UK population that is age 65 plus. So that means in terms of the number, it is a huge number. Yeah. So and then later on, we also find out from the survey that for 85 plus people, and then it will be doubled to 2.6 million by 2046. So it gives us the ideas that it is a kind of pressing concern if we are not going to provide some solution to improve the well-being of the elderly. And then because of the aging population, it will lead to different kind of concerns. For example, living alone as well as the social isolation. Because when we talk about social isolation, it will lead to many different kind of issues. For example, the mental health issue or the accidents happening in in the home place, so and so. So for this one, if we are going to look at some figures which will give us some ideas, what would be the actual concern? 3.3 million older people live alone in England or Wales. And then compare with the total UK population, the percentage, that is not much. But when we just look at this number, we know that this is a large number. And then over 2 million age, that is 75 plus live alone. They live alone, and then some of them, they don't even speak to anyone within a month or for a long time. Yeah, so that means when I talk about well-being as well as the mental health issue, that is mainly because of this kind of concern. And then when this concern that will propagate to many different areas. For example, when we talk about the healthcare, the healthcare usage, especially for the NHS hospital resources, and then we can just find out that 50% of the hospital beds are used by older adults, and then so there will be some chronic condition affect 50% of those elderly living alone. And then that will lead to some implication on economics as well as social challenges. For example, that is some pressure on the pension as well as different kind of services, as well as the housing issue, as well as the caring issue. So we can imagine that. So now, the previous slide I just mentioned about, I just give an overall picture about the old population. Now I try to move forward to talk about the concern or the issue about the fall among the older adults. So I will talk a little bit more about the impacts. So when we talk about the accident rate, and then we will just find out that fall are the most common accident among the older society. And then 1/3 of the older people, older 65, will have a fall per year. And then 1 out of 2, and then over 60 will have a fall annually. So in this case, that means because there are so many falls in the older society, we can imagine that it will affect the, for example, the increased use of the the NHS resources, and also there will be different kind of consequences of the falls. For example, when fall happens, sometimes they will cause the hip fractures or the bone fractures, and then that is the most common serious injuries. Once injury happens, and then we have to, there will be different kind of implication on the use of the resources, including the carers, including the hospital beds, and then so as well as it will affect the patient's mental healthy issue, as well as because I mentioned about the social isolation, and then because when people they fall, especially for the older people, they fall, and then they will lose confidence, and then they will just try to hide themselves, and then this will become a vicious cycle. That means they do not want to participate in any activities, and then they will stay at home. When they stay at home, and then the rate of the fall or the accident rate will increase. So this is the vicious cycles I just mentioned. Anyway, now when we talk about the injuries or the fatalities, and then fall are the leading cause of the injury-related death, especially for people over 75. And then so I mentioned about the fractures. So that means common injuries, including the head injuries, the hip factors, so and so. So in this case, the implication, as I mentioned, that is, it will increase the cost of the NHS. So what kind of thing we can do to support the society, to improve the well-beings of the older society, as well as help to really, to reduce the implication, the cost implication to NHS or other areas. And then there are a lot of things the academic can do. Yeah. For example, I'm going to talk about that later on. Yeah. So that means try to summarize a little bit what I have mentioned. That is the challenges about aging. So that means we just find out that when ages increase, we will lose our, the physical and the cognitive strength, and that will increase the risk of the fall. When risk of the fall increase, there will be different kind of implication on the society. Yeah. So the current solution, there will be different kind of the solution to help us to detect the fall or predict the fall. And so I'm going to show some slide about what kind of solution I'm going to, the academic has provided. But bear with me a second that when I turn it on, the presentation mode, and then the Zoom just cover some part of my presentation slide. I need to find a way to, okay, just a second. Okay. I think that, sorry about that. Okay. Okay, so let's take a look at about the current, the solution about the fall detection. Usually it is, we will have the wearable system, for example, a smartwatch, and then this smartwatch that is just to have some sensors to measure, for example, the tilt angle or acceleration. And then we just simply use a very simple technique that is threshold-based algorithm. That means when we have the acceleration that is more than certain threshold, we are going to detect that or to confirm that this is a fall. Yeah. Okay, so this is something very simple and portable and also affordable, but sometimes it is not very accurate to detect the fall. Another one that is some video-based detection. We could have some cameras to monitor everyone in an open area so that we would have some machine learning algorithm that is to detect whether the fall, or even we are able to use a sequence of the movement to predict whether the fall would happen. Yeah. So this one that is non-invasive. That means we do not need to have a wearable device, but that is intrusive. That is, we do not have privacy in that case. And then that would be different kind of way to improve the detection or prediction accuracy. That is something like the sensor fusion. We combine different kind of sensors so that we have integrate all this information and then try to use different kind of information to improve the prediction performance. Another one that is I think that is very popular in academic, that is to use the machine learning model to do the prediction. So when we use the machine learning model to do prediction, one drawback is that we need to trust the model. But how do we trust the model? Because it is a black box approach. That means when we are going to fit in something into the model, and then the model just tell us that whether this is a fall or not, whether there would be some fall will happen in the future. We do not know why, we just see the outcome. So that's why we need to have some algorithms to help us to understand better about the algorithm. Yeah. So that is the opportunities. We are going to develop some algorithms, that is the explainable AI or XAI algorithm, that will try to understand this kind of machine learning model and give us some ideas about the causality. That is, if I'm going to use the XAI term, that is transparent as well as interpretable. When we refer to transparency, it means that we try to come up with a model. That model will tell us the internal mechanism. Yeah, by looking at the mechanism, we will know when we have what I mean, that is how the model which is going to give us the outcome or the prediction. Yeah, and then another one, that is interpretability. It means that for certain input, we will have some ideas why that output is coming out from the machine learning model. Okay, so that means if the model is transparent and interpretable, that means from the user point of view, that is this model that is understandable, as well as to help us to develop the trust, yeah, about using this kind of black box machine learning model for some for different kind of applications. Yeah. Okay. Now this one, that is and now what I'm going to present, that is about this paper, yeah, from our group, that is Liang, me, as well as another collaborator from informatics. We develop an algorithm which is called the hierarchical fuzzy model agnostic explanation. And then this is a kind of algorithm which is going to explain the model, just like the diagram right here. Look at this diagram. This is a closed box model or black box model. So that means when we are going to fit in something into the model, for example, a sequence of the movement, when people walking so and so, and then we are going to fit this sequence into this model, and then this prediction, that could be different kind of prediction. For example, for a window of time, and then according to the input, the walking sequence, we are going to predict that in the future, maybe in the next second, this person will have a fall. Yeah, so this is the prediction. And then the next one, that is just a binary classification. By looking at this sequence, and then now we have a fall or not. So the output, that is going to confirm that that is a fall or non-fall. Now, why this is so important? It is because that if we are able to predict in the next second that a fall will happen, it is possible to use different kind of control theory or different kind of protection mechanism, so that which help people to balance themselves. That means to turn a fall into a non-fall. And then another one, this one, that is because we mentioned sometimes before, that is the false positive or the false negative, which will be very expensive. Yeah, but if we have some ideas to make sure that by looking at some evidence, this evidence that is given by the explainable AI, the cause of the fall or not. I mean the cause of the fall, to confirm whether this is a fall or not. That means that will strengthen the user trust to confirm whether the decision made by the machine telling us whether this is a fall or non-fall, just to build up this trust. Yeah. So that means from this bunch, that is the machine learning model we use, yeah, and then now we have another thing right here, that is we are going to collect all the information from the closed box model and use this FMAE. Again, FMAE, that is the fuzzy model agnostic explanation. That is an algorithm which is going to provide us some explanation to help us to develop trust, yeah, whether the decision made by the machine learning model is true or not. So now the FMAE, which will give us different kind of level of explanation. Yeah, so I'm going to give the scenarios to help us understand what does it mean by the level of understanding. Yeah, and so if you are interested in this paper, probably you can get a better ideas what kind of explanation this model is going to give us. So we will have some sample, local, domain to university level, and then we are going to use we will provide semantic explanation. That is, for example, we are able to turn some numerical value that is difficult to be understood by human, and then turn it into some linguistic terms or some language, for example, using the large language model to help us to understand why this happened, according to what mechanism, and then the output, the model output will give us, for example, a 4 or ln 4, yeah? So and so, yeah? So I think that it would be good to look at some scenario, and then this scenario will help us to understand what I just talked about in a better way. Yeah, so I just I just use this slide to help us to develop a better picture in our mind. Okay, now we have a black box models right here, and then the input, I'm going to use the tilt angle of the body as well as the acceleration of the body, and then the output right here, that is the whisk of force. For example, I'm going to quantify that to 0 to 1 range. For example, if 1, that is a high whisk of 4, 0, that is the lower whisk of 4. Yeah, so I just simply use different kind of linguistic variable to describe the 4 whisk, low, medium, and high. These terms, they are understood by human. Yeah, so the same for the angle as well as the acceleration. For this one, we call this is the local level explanation. By local, it means that I'm going to talk about a range of these parameters, a range of this input. For example, the angle, the tilt angle, that is in between 70 to 85. Yeah, so I just make it a very large tilt angle just to help us to better grasp the idea. And then the acceleration, that is from 8.5 to 10, something like that. Okay, so the FMAE algorithm, that is trying to extract this information from the black box model, and then when the model, that is, they are working in this range, we are going to extract the information and represent this information. What I mean the information, that is the internal mechanism of the black box model, and then explain that using some fuzzy rules. And then these fuzzy rules, they are very close to the natural language that could be understood by human. Yeah. So that means when the angle as well as the acceleration happen in this range, the FMAE method, they just find out that we have 3 rules to explain the output. The first one, for example, yeah, so for this case, I think it is pretty straightforward, and also it looks like that it is a common sense, but we can extend these ideas to something more sophisticated, and then the FMAE is going to extract some internal information and put it into some format, if then root, so that people can understand. Yeah. Now for root 1, the tilt angle is large, acceleration is high, and then the 4 whisk is high. So I think that it makes sense to us. Yeah. So this is something like a common sense. Yeah. But now this model is working like a common sense. So that means we can make sense that this model is working in a good way. Yeah, so that means rule 1, rule 2, rule 3, we are going to use the angle large, moderate, small, and then the acceleration high, medium, and low. That will tell us that the whisk of 4 is high, medium, and low. Yeah, so this is a method to explain what is happening, the working mechanism of the model. Yeah. So if we are going to use the large language model, and then it is possible to tell us a little bit more, that is to translate some these rules into something more detailed, so that the human beings, they find it more easy to understand. For example, it is possible to put it in this form, that is to observe the patterns, and then this pattern that would be high fall widths are frequently linked to a large tilt angle combined with high acceleration. Yeah, so that is represent in this point form so that we are able to understand the model behavior. And also, it is possible to use some semantic explanation. We are able to use the large language model to translate that so that this explanation that is suitable for different stakeholders, for example, the patient, or I mean the carers, the researchers, and then the clinician, so that different people will get different details to understand the behavior. Yeah. So I think that okay. Yeah. So sorry. Okay. Now I'm going to move on to the next scenario. Yeah, the previous scenario, that is a local level, that is we consider a range of the tilt angle and a range of the acceleration. And now I'm going to talk about the sample level. That means that is this diagram. We have different level of explanation. And now this is the local level. The local level, it consider a range of the acceleration, a range for the tilt angle. And then so now I'm going to go down one layer lower. That is, I'm going to consider a particular case. This particular case, that would be, for example, when we are going to detect for, and then for that particular case, the tilt angle, that is 75, and the acceleration, that is 9.5. And the model tell us that the fall happened. But how can we understand whether this decision is right or wrong? And then we will look at this particular case. And then we just find out that previously we have three rules right here. If the angle and acceleration, they happen in this range. But once we find out that in this particular case, 75 degrees as well as 9.5, only this rule contribute to the prediction outcome or the model outcome. That is, the tilt angle is large and the acceleration is high. That means only the rule one is activated. So in this case, we know that why we are going to predict the fall risk is high. It is mainly because that the tilt angle, that is, fall belong to the category of large angle, as well as the acceleration, that is, belongs to the high level. So using these rule style, it is possible to help us to translate the complicated behavior of the model into something the human beings they are able to understand. Yeah, so that means, again, if we are going to expand this rule, it is possible to have more detailed explanation. For example, observe the pattern, as well as try to use this value to give us further explanation using different wordings, yeah, subject to different users. So something like this. According to the fuzzy rules, these conditions strongly suggest instability. Yeah, so that means we are not going to stick to the term angle and acceleration. We are going to use instability. Maybe this term that is easier to be understood by different group of user, and then it is possible to give us some summary using the large language models. Yeah. Okay. Now potential application. I just mentioned about the fall risk prediction or detection. It is possible to extend this to different kind of applications suitable for the aging society. One of them that would be the lower back pain risk analysis. We know that there are a lot of data set available from the internet, and then we can use it to train a model, and then this model will use different kind of input, for example, the EMG measurement, the posture of the body, so that this model will tell us that the risk of the development of the lower back pain. But basically, this is a black box. Even though we know the level of the risk, but we do not know why it happens like that. And then the FMAE, it is possible to give us the explanation, to tell us the working mechanism, as well as the model behavior. So these information, they are very useful. For example, the physiotherapist, they can use this kind of information to understand a particular case, for example, a particular patient, so that they are going to develop a bespoke therapy to that patient, as well as for example, for researchers. And then some situation, we cannot make sense of the output because we do not have sufficient knowledge about the model or even the sufficient knowledge about application. But using the FMAE, it is possible to translate this kind of complicated application into some rules. They will give us some more knowledge to understand better about the scenario as well as the application. Yeah. Another one, I just name a few more right here, but not limited to this. Maybe one of them, that is the gait and balance analysis, and then the sleep quality assessment, the cardiac health monitoring, as well as the rehabilitation progress tracking. So these kind of things, and then so we can name a lot of them. We can use the machine learning model to improve the well-being of the older society. Yeah, but the same thing, that is the closed box approach, which cannot give us much more information about the working mechanism of the model, and then we are not able to trust these models, and then this will prohibit us to stop us to using this AI technology for the society. Yeah. So so I'm going to have the final conclusion. That is, today's talk, I mentioned about the challenges in the aging society. Yeah. And then the role of the MAE, that is the FMAE, which provide us the explainable approach, which help us to understand better about the model behavior. And then this model behavior, if it is transparent, and then it will help us to build up user trust, and then we are going to use this AI model in different kind of areas, including the old population in the UK, and then some now a broader impact. That is, when we are going to deploy this system into the old population, it is possible to help us to reduce the use of the NHS resources, as well as to release the burden from, say, the caregivers, so and so. And this is the final thought, that is about the XAI, something like the FMAE, that is very useful to address the aging society challenges in different way. Yeah, we can think of. Yeah. So today's talk, I just mentioned the tip of the iceberg, how FMAE can help us to improve the user trust of the AI technology. But this kind of thing, that is using our imagination, creativity, I think that it will extend the impact, not only on this area, but many AI areas as well as application. Yep. So so I think that this is the last page. Thank you very much for your time listening for this presentation. So if you have any questions, I'm very happy to discuss.
All right, thank you very much, Lam. That's very great to see the advance in XAI, inspired from the definition of artificial intelligence to the fuzzy concept and even more applications in aging society. That's good to see that. Since our time is limited here, we might have more discussion in the panel discussion, right? Okay. I think it's time to move forward. I'd like to introduce a bit about the next speaker, Dr. Wei-Yong Si from University of Essex. So you can share your screen, Wei-Yong.
Yeah. So okay. Yeah. Hello. So can you see my screen now?
Yeah.
Okay. Thank you, Ziwei. And I'm Wei-Yong Si. Hello, everyone. I'm Wei-Yong Si from University of Essex. And I'm glad to join the ECR webinars, Control Techniques in Human-Machine Intelligence. Today, I will talk about the robot manipulator skill learning and generalizing through collaboration. So first, I would like to introduce myself and my robotics lab in University of Essex. I did my PhD in Bristol Robotics Lab since 2020 and graduated in 2023. After that, I joined University of Essex. Now I in the computer science, electronic engineering department, and robotics group. Currently, I lead the intelligent robotics and the interactive system lab. So in our lab, we have various cobots such as Frank robot, Bax robot, Dobot, and nanorobot. Also some vision system and haptic device, some things. And I also want to, two other projects I are working since joined the University of Essex, and two about robot assisted healthcare, specifically robot assisted tracing. Oh, so as you can see, the first video shows the we're using the machine vision to recognize human pose and using by manual robot arm to plan the trajectory for the human and wear the dress for human bodies. And the second task project we are working the using Bax robot to waste the sortings, and this for the recycling applications. So currently we have various sorts in the recycling company, so they want to employ the intelligent robotic solutions for the various sorting. So currently my research mainly focuses on the robot manipulation skill learning and the human in the loop mechanism for robot learning. And the third is the compliant interaction control. So and we also explore various applications such as the recycling environment and healthcare, flexible manufacturing, and agricultural. So about the robot learning through the human calibration-based human demonstration, the background as this picture shows the various tasks, medical examinations such as ultrasound scanning, rolling doff, or manufacturing composite layout. Human has the excellent manipulation skills on this context-rich task. We want to explore how to transfer the human skills to the cobots. So currently there's some specifically my research focuses on the imitation learning from demonstration. Roughly there are three methods for the human demonstrations: kinesthetic teaching, calibration, and passive observations. In my research, we adopt the calibration-based method. The advantages for the calibration-based method that the calibration overcomes the limitation of physical workspace and also can capture the multimodal information such as human pose, EM signal, or force interface. And beyond that, the human in the loop is also provide online correction, interaction, such things. Finally, they can also provide adaptive mapping skill between the master and the follower robot. So we explore the collaboration-based demonstration. So the roughly the method we studied that this big shows in the human side we using the various device such as the HAP device, VR, AR, or imaging signal, image sensor, the multimodal interface. And on the robot side, we also have some sensors such as the force sensor or some tactile sensor to detect the robot environment interaction. So we collect all the data such as the control command or multimodal feedback. So we based on the data and using machine learning model to encode the human skills. So we then in the next stage we based on the robots the skills, the manipulation skills, the robot can autonomous or semi-autonomous execute the task. So that's the basic technology we use, the calibration based robot learning from demonstration. And yeah, about this, we have a review paper published in the IET, Cognitive Computation and System. So the first work we did that developed the multimodal calibration system for the ultrasound scanning. So we using the 3D mouse and the HAP device to capture human skills and using the Frank robot and to human control the robot to detect the human skills, and we evaluate the human interface based on some metrics. So take ultrasound scanning as examples, design the true interface with quantitative assessment for this one, because the multimodal calibration system is the foundation for the human robot skill transfer learning. So we based on that we find that we can develop the shared control to improve calibration in performance for uncertainty surfing scanning, ultrasound scan. So we using the shared control method to collect the human demonstrators. In this, we human only control the translation. The robot can based on the detector force to autonomous adjust the orientation. So they also expect the desired force along the z-axis to keep 10 Newton. So we compared the fully calibration and the shared control method, and we find the shared control solution is better than the fully calibration. And yeah, so the next we also explore the human in the loop for compliant skill learnings. So you can find this model we based on the dynamic movement primitives, but we improve this. We add human interaction terms based on the foundation DMP models. The H dot, this term can be training online to update online. So that means when humans to correct the robot's executions, we can collect the human correction signal, and we based on that to modify the robot skills. And yeah, so that's the control system for the rolling dove. We developed a hybrid force position controller. And next, we want to explore more so that robot can autonomous based on the perception enhanced contact reach. That means we using the machine vision to detect the shape of the dove that can autonomously to determine the start point, the outline. The task is robot to rolling the dove to a specific shape. So this is the big structures about our solutions. We developed these vision-based recognitions that can detect the real-time dove shape, and based on the perception output, we can sequence the skills and also can online execution our the robot skills. Yeah, this video shows And this is the task we did. The robot autonomously rolling the door. So they can based on the visions to determine around the forward, back, or from the side to from left to right. So that based on the machine vision. I think I will also explain the projects in the video in the post sessions, and due to the time limit, I just move on. Yeah, we compared the result and the desired shape and the desired shape and the actual shape, and we find the accuracy is pretty good. For the ultrasound scannings, we also using the imitation learning to collect the data as mentioned. We training our models to do this. As you can find these videos, this is ultrasound probe, and they get scanning on the phantom. They can detect this is the desired features. We wanted to detect the white point in the center. So yeah, this is the robot assisted ultrasound for the phantom. We also do this on the human human bodies. Yeah, as this video shows, the robot can approaching the human neck. This is the express narrows. In the left right video shows is this is the desired feature. This is the versal. So we want to detect this. So we're using the imitation learning to detect the human pose to do this one. Yeah, we further to wanted to consider some scenarios. For example, human motions. We're using the camera to detect the human motions. We're using the ULO to detect the human pose and estimate human motion. Based on that, we designed the adaptive motion trajectory planning to tracking the human pose and approaching that. This is the experiment scenarios. In this case, when the robot approaching our human bodies, when we motions, they can also react to planning the trajectories. We also get the desired the arteries. You can find this is the real time ultrasound videos. Beyond that, we explain the reactive adaptation for the multi-step task, such as using the Baxter robot to pulling a stuff from left to the right. So during the robot executions, human disturbing that, so they can detect the disturbance and they can react to planning the trajectories. Even though the human changed the design pose. Yeah, finally, we can also complete this task. So they use the reactive adaptations for the trajectory plannings online. And we also explore because for the medical examination task, the safety is quite quite important. So we developed the dynamic system-based skill modeling, so that can encode our motion skill for skills. So they developed the flexible neural energy functions with unique minimum for globally stable demonstration learning. So we also demonstrated these models on the medical robot ultrasound scanning. So this work published on this IEEE transaction on robotics. This is the details. We demonstrate only 5 demonstration trajectories from different points to the target goals. So we training our models, they can reproduce the skills and also can generalization. One more thing that we can also consider some obstacle avoidance, such as we can give the constraint the working space. The robot can avoid the obstacle. And one more thing, another work we developed impedance learning for human guided robotics in contact with unknown environment. In this task, and the robots can based on human demonstration. When human demonstration collaborations dragging the force sensor to demonstrations, the robot can learning the human intention and then can learning the impedance to compliant interaction with the environment. So the impedance learning for human-guided robotics in contact with the unknown environment. So this is an experiment. This way is for polishing the environment is unknown. So they can, based on the human demonstration, they can learning the human intention and also to update the impedance parameters. This work published on the also in attribute transaction on robotics. Yeah. Oh yeah. Finally, we have some designed some soft suctions for the robot grasping various shaped objects, such as the soft sucker can grasping carp, vegetable, or some tools. It has various shape. And finally, we conducted experiments using the flying robots equipment with the soft sucker. They can play the toys. Yeah, so we can find that the sucker and the intelligent robots can picking the various shape of toys and they can play designed positions and they play the toys. Yeah, so thank you. That's all my presentations. Yeah, is any questions?
Yeah, thank you very much, William. So any questions from the audiences can also raise your hand or just attend our panel discussion. So I believe the two speakers will be free to join our panel discussion, right? Okay, so I would like to give my microphone to Mike. And Mike will lead the Meet the Industry session. Okay, Mike.
Thank you, Zero. Thank you very much. So we have our second Meet the Industry session. And for this, I believe we should have present TG0, Kwanzaa, and Pinweld. And there are a couple of key questions that we would like to ask for their thoughts of industry in this context. And the first of those is related to challenges and innovations in teleoperated robotic systems. What do you feel are the key challenges? Latency, fidelity, development of intuitive and user-friendly human-machine interfaces, etc., but also acceptance, I think, within the clinical fraternity as well for these devices and tools. So, if our industry colleagues could please possibly offer us some thoughts on those, that would be greatly appreciated. TG0 representative here, Zero.
Hello, I'm Liu Chengguo, and I just maybe we can have a short introduction about ourselves. And so I'm Liu Cheng.
Yeah.
I'm the co-founder and the CTO of TG0, and we are a London company, and we are working on the HMI for the robotics and for the I mean, from many different areas, but robotics is one of the main area we are working on. Yeah.
Okay, thank you. Okay, thanks
Yeah,
very much.
we have Dan as well from Concert.
Yep.
So yeah, Dan here. Can you hear me?
Yeah, I can. Can you hear me?
Great to see you. Yeah. And
Yes,
so Dan, would you mind introduce a bit about Concert UK?
Yeah, so Quanz is actually a Canadian company based out of Toronto. We've recently, in the last year, formed the UK version of that company to support the growing AI, robotics, control and applications within the UK universities. And part of my role is really, as a company, our main customer is academics. 95% of our business is academic research and education. And so a big part of what I do is going around building relationships and partnerships with universities to look at these areas of interest. So yeah, keen to take part in the panel. I don't know if you've got one more person that wants to introduce themselves before we answer the questions.
Is anyone from Pinwell, Sue?
Well, I'm in the decade from Pinwell, might be not available for our discussion, so we could just skip him and start our discussion.
So just going back to what do you feel both of you are the key challenges and innovations in teleoperated robotic systems?
Yes, I guess I'll jump in there and give our maybe a slightly different perspective. Being a company that provides technology to universities to do these types of research, typically we're not looking at building a product that's going to go to market. Our market is an academic researcher using it to carry out their research. And so some of the challenging innovations have kind of come up in the previous conversations around latency, about edge or node compute to be able to keep the control loops tight. I think from our perspective, there's a couple of challenges that we see outside of that. One of the key ones is actually attracting intelligent people into the space to work on these problems. Whether we like to admit it or not, control isn't maybe as sexy a topic as we would like it to be, and it maybe doesn't draw in as many people to learn it. And so a big part of our company is making products and access to teaching material that really encourages people to take part in these topics. And actually what this ACE network is doing around finding the 4 key areas, and one of them today's topic being kind of the aging population, it's really key to tie the technology with those everyday problems, because that's how you get people encouraged in this area. And so it's been enlightening listening to the presentations today and seeing everyone's different way of looking at certain pieces, and then a lot of things that are very similar. And so, yeah, first key challenge for us is getting people into the area. Once you have people in that area, there is some technology pieces that need to get worked on, and some of those again have come up in the presentations. The previous presentation from Wee Young from Essex University was interesting to see about some of the control loops they were looking at implementing, and it highlighted for me one of the key areas that we see as a challenge is when you're using industrial robots and you want to create a new control mechanism, but the black box of this industrial robot doesn't allow you to get in and change the controls. And so that's been a key area for us working with academics on, can you reuse industrial robots? Do you need a different robot? How do you really get inside those black boxes that are the control box of robots, and understand how you can start inputting your intelligence, whether that's AI intelligence, whether it's your new control algorithm you've developed. And so that's an area that we work with a lot of academics on. And so that's a piece that we've found very useful. And then I guess the third point I wanted to mention was around AI. Everyone's talking about AI. It's a hot topic. There was even some more press about it the last couple of days with the release of another new model. And so it's an area where we get a lot of questions, and we have a lot of questions for academics as well. And actually a big part of that I've seen, especially in the last year, and it's been happening for many years, but I've seen a lot more of it in the last year, is this idea of computer science departments and engineering departments working a lot closer together. Historically, computer science, computer engineering, they've been doing AI for many years. The same with kind of control-based engineering departments. AI is not a new thing. It's new for the populace, but it's not new for them. But they have less likely to have been working with hardware in those departments, whereas more traditional engineering departments have spent years interacting with hardware versus software, but maybe haven't got the experience with AI. And so actually, for me, overcoming some of those challenges of bringing those two departments together, and universities like Essex, Hertfordshire, and a number of others have already brought those departments under the same school, which makes it a lot easier. But I see that being a big driving factor for a lot of these subjects is those departments working closer together.
That's great. Thanks, Dan. Thanks very much indeed. That's very insightful. Liu Cheng, any
Yes.
comments?
Yeah. So our company a little bit different with other companies. So basically, we are mainly focused on the commercialization. So I think the challenge here I want to emphasize is about the commercialization. So I think today people talk about money, the very good ideas, and how to maybe finish some tasks or do some like a research, up-to-date research in this area. And I think so if we talk about the long-term the destination, I think it will be how can we make this technology ready for the market, and how can we promote this technology to a worldwide market, not just in one area. It should be worldwide used. I think this is something. So even our company, so when we have some internal research, internal R&D projects, probably we use very good technology and is get overwhelmingly recognized internally. But when we trying to push it to the outside, trying to sell it to our clients, and we find out the market needs and our own internal output is a little bit different. So the desire from the market and the output from our company sometimes is mismatched. So I think so if we talk about some technology especially for long term, we really need to think about what is the market status and what is needed in the next 3 years or next 5 years or even 10 years, and then align with that. Then I believe that technology can have a maybe long-term lifespan, not just like 3 or 4 years ground application or ground funded project. Yeah.
Okay. Thank you for that. That's very helpful. Thank you very much indeed. So moving on and linked to entrepreneurship in automation and device development, etc. In terms of pathways to commercialization in the UK, how do you feel that work? How well does that work, should we say, in the UK at present? Are there any barriers there, particularly funding and IP challenges? I wonder if either of you might be able to comment on those.
Yeah, so I can jump in there with some comments. So as a company, as I mentioned earlier, being Toronto based initially, we've been going for 35 years, and we have a vast experience of working with the government agencies in Canada and the US, and that's something we've spent the last 2 years or so doing more research about in the UK. And it really talks to this around pathways to either commercialization or even just the research itself. And so we've been looking at projects that won't be new to anyone here, but things like KTPs, where actually the IP tends to live very heavily with the company. And so that seems to make a lot more sense for working on a commercialization project, because they seem to be funded very easily. And so it's a great way to get that expertise between academia and industry. And it's something that we're looking at for how we look at building an R&D team locally in the UK potentially. And so that's something that I feel seems like a great success and something we're looking at to do more of. And then the other side of it is we've been going to lots of different meetings with different funding agencies, different universities, and working out where as a provider of technology, but also someone that wants to develop their own technology, how we fit, because there's 2 roles in which we can play. We can be a provider of technology that enhances the research, or we can be a true partner where we want to develop a new product locally in the UK, and we want the expertise of the UK academia as well as the UK funding to be able to do that. And so we're learning every week more and more about this. And actually a comment from the previous speaker about the idea of the market needs and the industry or the academic wants and desires, and joining those 2 things together can be difficult. We struggle with that the same way in our own R&D team. If you let the R&D team run wild, they'll create fantastic products that they absolutely love. Is anyone going to buy them? That's a different conversation. And you find that with university research, you don't want to stifle the research, the blue sky thinking, the research that comes up with all these. You don't want to stifle that, but you also want a route to industry. And so you have to accept that some projects won't make it to industry, but how do you improve that that transfer rate between blue sky thinking and moving along the technology readiness levels. And industry has a big part to play in that, and that's something that we're trying to understand more in the UK as to how we can be a big provider of that. And so I think a lot of it comes down to events like this, open communication, finding ways in which today I've learned a lot about how a number of academics in the UK are working on this teleoperation in the health sector. If we were being open as a company, the health sector isn't a big space for us. But seeing how the technology is being used is exactly how it would be used in a warehousing application or a logistics application. It's the same types of technology, just used in a very different way. And so, yeah, it's a roundabout way of answering the question, but I think for us, we're still learning. But I think the funding routes are the way to go, and really opening up communication between research and industry, and really partnering and finding ways to do it together.
Okay, that's great, Dan. Thank you very much. Liu Cheng, do you have any additional comments?
Yeah, so I think I totally agree with Dan's idea, and I think it's one thing I highly suggest is for many universities, so and many researchers, I hope they can talk with the SMEs or talk with other maybe big companies from as early as possible, and try to connect with industrial partners. The reason is, as I mentioned, so there will be a gap between the academic and the outside industry. So I suggest if you have the resources, yeah, please contact them and try to understand their needs. And in that case, it's probably, first of all, it's probably help you understand what is the real market needs. And secondly, if you apply for grants, probably with the input from the SME can help reshape the proposal. And thirdly, I mean, talk about the commercialization, and if they can get involved as early as possible, then in the future they can be ready for the commercialization. Yeah, thank you.
Brilliant. Thank you very much, both. So I am conscious of time, and so I know we've all got some videos to see from posters. So thank you, both of you, Dan and Liu Cheng. Thank you so much for joining us today. It's been really very helpful and provides some great insight from an industrial perspective. So thank you very much, and hopefully you'll be able to join us for our future meetings and activities within the network. So that would be great.
Sure.
So, sure. Thank you very much indeed.
Thank you.
Thank you very much, my old friends. Thank you. Okay, so let's now move ahead to the poster and visual showcase. We're gonna have 5 presentations from Birmingham City Uni, Lancaster Uni, King's College, and Essex. So let's start from Birmingham City Uni. Are you ready to share your screen, Hassan?
Yes. So do you want me
Okay.
to share the video or the presentation?
Oh, you can start from the poster demonstration, and if necessary, you can talk about the videos as well.
Okay.
Sorry, we can't hear you.
Okay.
Yeah, feel free to share your screen when you are ready.
Yeah, that's really Yeah, sorry, yeah. Can you see my screen now? Okay. Okay. Okay, so I thought it's I have to record a video. That's why I already got everything in the video, and that's why it took longer. But anyway, I can go. Yeah, I'm trying to stop the video. Yeah, hopefully that one works. Okay. So yeah, I know I got 4 minutes. So I start the first topic about the context-aware intelligent network design. So as you're all aware, with the modern networks, there have been multiple dynamics parameters, including data rate, coverage, latency, and there's a need to understand the context to make sure that we match all those multiple dynamic parameters. The second point we need to highlight is the current system is kind of shifting from purely technical optimization to a user experience-driven system, and that's why we focus on this work to understand more about the context of the system when it comes to the design, considering multi-context, multi-vendors, adaptability to the system. That's why in our system we focus on 2 use cases, which is resource allocation and spectrum management. In our system, sorry, it's just I need to go back. Okay, so the first one is resource allocation, where we use 2 methodologies. The first one is meta learning, and the second one is reinforcement learning. The whole idea is we pack more of the relationship and the tasks between the tasks. We provide a relationship in the process in order to understand about the context. And we pass that information with meta learning, which managed to understand the context, and then we did the resource allocation. Almost same idea has been considered in the reinforcement learning, that in reinforcement learning, we provided a real-time data during the reinforcement learning to make the resource allocation adapt to the system. So jumping to the second use case to support our system, which is spectrum management. Spectrum management, we have used 2 different techniques. First one on understanding the ideal time for data processing. So in our system, we provided some real-time data considering with that spectrum adaptation system in the context. We almost have done the same thing when it comes to cognitive radio networks and the spectrum management. So when we did that, we're trying to emphasize the need. We emphasize the need to understand the context behind the whole system. That embedded context managed to give more information about the context, making sure there's an adaptive learning. This is moving forward to go out from only a user-centric system to multi-perspective, which goes to the human, which comes to our proposal where we have human-centric intelligent network. And the second part falls within a human-centric intelligent network, which is we provide personalization and adaptability system. Hopefully, we could be able to create a richer interactive experience for operators, which can transform the networks into truly adaptive user-centric systems to redefine the more personalized adaptive solution for telecommunication. Thank you. Hopefully, I didn't exceed my time.
Well, thank you, Hassan. I think it's fine. Yeah, and maybe we could discuss something after your second presentation, because I think they were sharing the whole story. Maybe you can just move ahead.
Okay. So now I'm more relaxed. So in the beginning, the first presentation was about context-aware system. So now we're going all the way. So from only understanding the context of the scenario, where we're going all the way to human-centric intelligent network, HCIN, where we not only consider the user experience, we consider the context user experience and provide more, I would say, more personalization, adaptability to the system. So our priority here to highlight the user experience, personalization, adaptability, and also keep in mind the traditional KPM. We have used intelligent chatbot, telecommunication chatbot system to emphasize our point. The current system lack from low user satisfaction as well as inefficiency in the proposal. That's why we proposed two, I would say, LLM-based chatbots, intelligent chatbots. The first one, ORAN, which were trained on documents coming around OpenRAN system, from installing, maintenance, providing technical information and the specs from different vendors. All those documents have been passed to the system to train on, and we managed to have an assistant who can support the operators, maintenance team, engineers, and different. The second chatbot system, which is based on Telekna dataset. It's a dataset that has questions around telecommunications in all stages. So we used LLM model to train the model to provide, I would say, a system for operators, engineers, researchers, everything to understand more about the system. Going to the next level of intelligent chatbot. So actually, this is like a current running KTP project with a company. So we are not only focused on having a chatbot which deals with human operators or whatever. We going to the next level where we have a chatbot system that's linked to IoT data and have two different access. So the system has IoT data, which goes towards to have some pattern understanding and the behavior of the data, as well as patients' history data. And all that data passed to the intelligent chatbot, which give two access, either for physician management through giving more analytics or more, I would say, more details about the case based on the historical data, but also has a second access to the patient to give some kind of recommendation based on the based on his health status. And thank you for listening. Happy to take questions.
Okay, thank you very much, Hassan. So any questions from the audiences? No. Silence. Okay, Lan, please.
So thank you very much for the presentation. Can I ask a question about the training of the large language model? Because I think that it will, I mean, the computational complexity or the computational demand that is very high. And then even though we are going to fine-tune the large language model, can you give some, please, could you give some insight about what would be the best way to train the large language model that make it suitable for example, you mentioned about the generative AI model.
Yeah, this is a tricky question. And actually, we had one use case that we couldn't actually do it because of the issue you have mentioned, which is the standards. There have been lots of potentials where people can use ChatGPT on retrieving standards, even to some specific releases. But because of the computational problem you mentioned, that couldn't happen. So what we did is we focused on the key parts of the documents, and we used optimized llama model for using that. But even though I know there are lots of limitations, but yeah, I don't have a magic answer to respond to this. But yeah, it's still bottleneck when it comes to LLM usages.
I see. Yeah. So can I ask one more question? Yeah, because when you mentioned about the large language model, it means that we are going to take advantage of the existing knowledge embedded in the large language model. But I'm thinking about that for some specific or custom application, why do we need to have a large language model? Basically, we are able to just trim down the model, and then so a large language model become a small language model that is more accessible to the application we just discussed.
Okay, so are you proposing to use small language model?
Yeah.
Are you talking about a specific use case I presented or in general?
Yeah, because the application you mentioned, that is a specific use case. I think that why maybe it is, I mean, more practical to use a small language model.
Yes, I know what you mean. So basically, when we talked about that medical application, so probably because when I was presenting, I was a little bit nervous. I didn't mention that part, but also the patient get to see, I would say, a report, written report of all generated information. And somehow the large language model supported in providing more context when it comes to generating that reports. I know what you mean. If you use Phi, for example, which is one of the small language models, that might be more efficient and even lighter. The Telakna, so I haven't tried that for myself, but I feel like it gives more context. Even when we talked about the Open RAN or the Telakna dataset, both of them, they also somehow they get some background information from like the previously trained data, but definitely small language model might work. And actually it may avoid any biases when it comes to generating data. So that's something we can try.
Right, I see. Yeah, so there are pros and cons to use this kind of models. Yeah, thank you very much.
Okay, so thank you both. Let's move on. Welcome the posters from King's College London. So, Feng, are you here?
Hi.
Well, yeah, please share your screen when you're ready for that.
Yeah, sure. Okay, so basically I have a pre-recorded video, so now I'm gonna show my video. Oh, sorry.
Well, if you need more time to get prepared, can we just go to the next and you can wait for the next? Is it fine for you?
I'm sorry.
So I mean, if you need more time to share your screen or get prepared, can we just move on to the next and you can join accordingly?
Oh, I'm sorry. I thought I was playing the video. Sorry about that.
And no, yeah, we didn't see your screen.
Oh, okay, sorry. I clicked the wrong button. Oh, can you see the video right now?
Yeah, we can see your screen, and you can just mention anything during the screen, please.
Okay, so right now I'm going to play the video. Yeah,
Okay.
can you guys see the videos right now?
Yeah.
Okay, sorry about that.
Sorry, Feng, we couldn't hear your voice
Oh,
from the videos.
you can't hear the voice from the video?
Yeah.
Oh, just 1 second. You might have some technical issue because there's some voice
Oh,
in my video, but when I'm playing, I can hear the voice. But you mentioned you can't hear the voice, right?
well, so Would you like to just show your video and speak alongside your slides? Is that fine?
Oh, yeah, sure. So just 1 second. Let me open my
If
slides.
I noticed something when I shared. When I shared, there is a button. If you click on it, it's called share sound. So if you wanna try this, it might work.
Sorry, which button?
So we click share, and then when you pick the screen, there's a button called share sound.
Yeah, I saw that.
Might work. I'm not sure.
So can you see the video right now?
Yeah.
Yeah, so hopefully this time you have sound.
Hi everyone, my name is Feng Zhang. I'm a PhD student from King's College London. Today, I'm going to present my project, an obstacle avoidance specific reinforcement learning method based on fuzzy attention mechanism and heterogeneous graph neural network. Obstacle avoidance navigation control is meant to drive a mobile robot from a random initial position to a destination point. There are two major approaches to designing a controller for this. The first one is the classic method with a predefined controller. The second one is based on the reinforcement learning method, which makes agents learn how to drive by interacting with the environment and obtain as much reward as possible. But this method has one common issue: low data efficiency. Modifying the network structure is a simple but effective way to increase data efficiency in reinforcement learning. The core idea of this branch of method is to apply unique network structure to extract actual information from the raw data. Rather than using MLP, people start using recurrent networks or LSTM to extract the temporal information, and use graph neural network to extract the structural information. But the question is, can we further improve this? In a graph under the graph neural network context, there are many edges, and the most existing graph neural networks treat them equally. However, under an obstacle avoidance scenario, different objects could have a different importance when we make a decision. In other words, we should treat different nodes and edges differently. Therefore, we introduce a fuzzy attention system to emphasize those edges that connect to components closer to each other and weaken the connections where two components are far away. Here is the overall structure of our method. Rather than feed the raw observation to the MLPs like what most reinforcement learning methods do, we first create a graph based on the scenario and then process the raw observation with a fuzzy attention mechanism-based graph neural network. Finally, we feed the structural embeddings into MLPs to predict the actions and values like regular reinforcement learning methods do. In our experiment, we show that by adding a fuzzy attention structure, all candidates' graph neural network methods can have a better performance under the obstacle avoidance control scenario. It can even allow some GNN methods that completely fail in this scenario to successfully achieve their goals. By comparing with other baseline methods, our method demonstrates better performance with respect to both training efficiency and success rates of driving the mobile robots to the targets without any collisions. In conclusion, our method provides a simple solution for increasing the training performance of reinforcement learning by changing the network structure only. Here is a short demonstration that shows the performance under the customized by Bullet environment. From the short video, we can see that after training, the mobile robot can successfully reach the targets without any collision with the obstacles and smoothly and efficiently. Thank you for watching. That's all for my presentation today.
All right, thank you very much, Feng. So, any questions or comments on the presentation of Feng? If there's no, welcome Wei Yong again to give us a short video and the poster presentation. Yeah,
Okay.
you can share your screen.
Yeah. Hello everyone. So can you see my screen now?
Yeah, we can see your poster.
Okay, and hello everyone, and I will introduce the robot-assisted dressing system based on bimanual arm and machine vision. After that, I will play some videos from our lab. So as mentioned just now, so the robot assisted dressings is quite important, such as there are some solutions for robot dressing vision solution or dynamic motion learning or safe adaptives. So it's quite challenging for the robot to autonomously dressing for the disabled persons. We would like to explore the bimanual arm and machine vision and imitation learning, combine all these techniques in one, provide a new framework for the robot-assisted dressings. In our systems, firstly, human pose recognitions, we're using the deep learning media pi or some other methods that you need Ayuku marker to record our human pose. So you can find we can get to the key point and get to the things. We collaborate to the collaborations between the arm and the head, so we can based on this one to generate the to get to the desired pose for each key point. Then we're using the imitation learning models such as DMP, so generate the trajectories from point to A to point B, so that the things. So we basically based on these solutions, we can achieve the robot-assisted dressings. But in the future, we want to integrate some more, such as the haptic feedback or some dynamic motion trajectory generations for the dynamic scenarios, such as mentioned when the human motion in this case. And yeah, so next I planned. Zui, can you see my screens? Not play the video. Okay, cool. So I want to explore some, play some videos today in my lab, intelligent robotics interactive system lab, just like this, the robots with the sortings based on vision and to recognize different sort to different ways to sorting that. And this just we mentioned using the robot to system tracing for the human. And we also explained this large language model for the human-robot interactions. We're using the pre-trained large language model, so they can do such as this human just natural language input and using deep learning to recognize the command, and they can control the robot to perform these tasks autonomously. So picking the lemon to the human hand, such task. So they can do the various tasks. Okay, so next just mentioned in the human-robot interaction, especially for the compliant interaction, and the robot system autonomously. Yeah, this one we developed the human robot the calibration systems just using 3D mouse to control the ultrasound probe scanning on the phantom. You can detect the real-time ultrasound videos and also where to show the contact force. Yeah, this way we can control the robot, the ultrasound probe to approach human and detect the arteries. You can find these arteries autonomously achieve this. based on the imitation learning for the medical robot system medical examination. And also we developed the shared control method to using the touch to control the robot, control the probe to scanning on unknown surface. So finally, we developed the intelligent arm and head system to playing the tools autonomously. Yeah. Okay, thank you.
Well, thank you very much for sharing the rich information on your poster as well as the amazing videos. So the final video will be from Lancaster Uni. Are you getting ready, Ollie?
Yes, I'm going to share my screen right now.
Okay.
Okay, great. So I'm going to present this our recent work on embodied AI companion for efficient object handling in bimanual teleoperation. So motivation behind this this work is that the bimanual teleoperation is in welding and manufacturing face very high operator cognitive load and inefficient human-robot collaboration. So to achieve the goal that to control two robot arms at the same time, we actually have three kind of strategies to control two robot arms at the same time. One is what we call the single person bimanual operation. So basically, just like the previous talks about the bimanual surgery, just one operator controlling two robot arms at the same time. And also have dyadic, which means that's two people control the robot arm at the same time, one each control one control each. And we also got another one called robotic assistance, which is also a promising trend in recent years because with the development of AI technology. So that's where we are trying to propose. So we're actually proposing a framework called BTLA to integrate an LLM to drive the robot company. So the idea behind this work is that we find that the normally the robot partner will just control one robot arm, but that is not very intuitive or very efficient in terms of human robot human oriented interaction, because a lot of cases human and robot the role of human and robot is not I mean, for example, the human can grasp an object, which task can be regarded as a naive one, but for the robot, it's much easier for the robot to do such tasks because it can obtain the gesture from sensors, and it can grasp the object more accurately and efficiently. So based on these ideas, we're trying to propose a frame that actually can switch between the human and the robot, so that it doesn't has to be a fixed role that the robot or the human has to play. Instead, it's actually a task oriented, so that human can choose to perform tasks that is easier or more high level command, or that is difficult for the robot to play. So now to answer to validate such a framework, we need to answer first three questions. One is that whether this framework whether single person bimanual teleoperation is more efficient or easier than dyadic, and the results, the preliminary results is presented here, and we found that especially the frustration is very different from the single person bimanual operation, which we believe that it is due to the different levels of the two operators. And we also introduced this LLM-based framework. This framework does three things. One is that it will understand the operator's commands, and then the second thing that it will, based on the natural language, it will output the function, which, well, it's not actually the script, but it's a little bit higher level functions, and then it will, based on the function and also the environment observation, it will choose automatically what kind of sensors and data the function and to perform the task needs. So and then the third thing that this part human robot bridge will do is that it will feedback information to the human operator to inform the operator about the next move. So we compare these three single-person bimanual operation dyadic and this proposed LLM-based framework, and we found that this the preliminary results are all carried out in the simulators, and the preliminary results found that there's improved performance and reduced frustration levels. And we also the next step for this experiment is that we're gonna move this one to a real life scenario, and at this stage we'll improve that prove the difference between the single person bimanual and dyadic, but we didn't compare this one to other robotic partners and other frameworks. So the next step of this experiment is that we're going to do more experiments on real world experiment, and also to compare with different models and framework. That's it. Thank you very much.
Okay, thank you, Harry. So, any questions about the previous posters or videos? We could just spare some time to discuss here. And also, these videos and posters have been attached on our website so that you can visit it again after our webinar. Okay. If no, I would like to conclude our webinar. So just let me share my screen. Okay, so yeah. So as you can see here, in the first webinar of Aging Society theme, we already collected the advances in academia as well as the industry to discuss some questions and concerns with common industries. And we have the interactive sessions for the PhD students, PDRAs, and ECR researchers to have the connection in between. This is what we like to encourage. And in the following, we like to see some more activities held by our Aging Society, either GCRC or our ECR. So in the following weeks, we are going to have some workshops to encourage more active interaction, and we also have the intent to do some more in-person activities. And at that time, we could make some in-person connection, and that will facilitate some grant proposals. That's our blue sky ambition for the following weeks. So Fulfil, I see you are still here. Would you like to say something? Or Mike, would you like to conclude for our webinar today?
I'd just like to thank everyone for joining today. I think we've seen some fascinating presentations and discussions with industry. I hope as many of you as possible, if not all of you, will be able to join us in these future activities. Some, as Zue mentioned, will be in person, we'll keep everyone informed and let people know when dates are available and where likely venues may be. So please just keep watching our space and our website, and please join us in as many of these activities as you can and would like to join. So thank you very much for joining us today. It's been greatly appreciated. Thank you.
Well, a short thank you also from me, just to thank everybody that participated, and also Ziwei and Mike that prepared and did a lot of work to prepare this webinar. There will be follow-up activities as well, and in particular there will be a form that we will circulate among participants, because we really want to know your feedback and ways to support the early career researcher in the best way. So please keep up with us. There will be a follow-up. Thank you very much.
Thank you very much.
Yeah. Thanks for attending our webinar. We'll keep you informed if we have further activities, and we do in the next month. Yeah. So just keep in text. Okay. Thank you very much for coming.
Thank you, everyone.
Thank you, everyone. Bye.
Thank you. Bye-bye.
Bye.